Sure, let's start off. I'm sorry, everyone. The last thing we started with the Pascal's law. Let's go ahead with the theoretical question and then we'll do more. So let's say we have a system like this. So we have pistons of area A. And the space between them is filled with a fluid. And you're applying force F, force F, force F, and F. And let's call this thing as point A. In the second case, you have only two pistons. Third case, you have only one piston. Point B filled with liquid. Point C filled with liquid. Arrange the pressures at A, B, C in descending order. Otherwise, do keep your cams on. This is an easy one. So what are the answers for this? Now you need to understand something. Even though it looks like there are four forces, there are two forces and one force, right? If you just draw the FBD of the liquid, you will notice something. If you draw FBD of any of the liquid, right, you will notice, let's say I'm drawing the FBD of liquid C. So this is that external force. This will be the force due to the wall. This will be also force due to the wall. And this will be also the force due to the wall. And because the whole thing is in equilibrium, this must be equal to the force F only. So even though it gives you a feeling there are four forces here, two forces here, and one force here, in reality, if you just look at the liquid, this wall is also exerting force, this wall is also exerting force. This wall, this wall, this wall is exerting force. In all the liquids, the force is same. Is that making sense? Think of this way. Suppose if you don't apply force at this piston, what would have happened? The moment you apply pressure here, the liquid would have pushed this piston outside, isn't it? So basically, these forces F are simply behaving like, as if they're a wall. Right? So if you draw FBD of any one piston, this is how you find the pressure. If you just draw FBD of any piston, this will be pressure at A into area. It doesn't matter which piston you take, it will be pressure at B into area. It will be pressure at C into area. So if you see, the pressure at A will be equal to pressure at B is equal to pressure at C. Clear with this? So the main thing is that, the mistake is people think that there are four forces, there are two forces. This is kind of like this. If you remember in NLM, if you apply two forces like this on a wire, and if you tie a rope here and if you apply a force F, they are the same, isn't it? People think there are two forces. In reality, here also there are two forces. There is a force due to the wall. Clear with this? So don't look at the number of forces there. Pressure does not care how many forces are there, right? Whatever force the piston is acting, the same thing the wall also would do. All clear with this? Easy one, theoretical. Let's see one more. Next thing, bind force. So what is bind force exactly? When a body is immersed in a fluid, it experiences an upward thrust. Which is equal to the weight of the displaced liquid. You're getting it now? This thing would be, Srihari, first of all, right, you better focus on the class instead of, just continuously just, spamming messages in the group, right? If I didn't answer, whatever answer you said, if I didn't say yes or no, doesn't mean you should just keep spamming and disturb me in the middle of the class. You please focus and attend the class and understand about it, right? If you are really so worried about your answers, right, me telling you all that, do one thing. Every Friday I keep an exam. In that exam, you please score 90%. I'll be completely fine with that, right? So please don't spam randomly, right? If there is something, I will let you know. There is no issue with that. So please focus on the class. I'm not angry or anything, but I don't know why you just spam and why do you expect, like, for every thing that you reply, I need to tell you, yeah, you did well. I can't do that. I'm sorry about it. So please focus. Right? So yeah, I don't know why you're putting it in the open chat box also. So that's your problem. So please focus. It's fine. Someone typed a right answer, and if I didn't say it is right, it does not mean you should worry about it. Happens, right? It's not a tough question. So what is there? I'll give you a tough question, then you answer, then I will definitely say. So, but please focus here. You guys are here to learn. You really want to score and you want to do something, then every week I keep a test score in that 90%. So now the thing is, the story goes like this. You must have heard about this thing, right? Archimedes. You know what is Archimedes famous for? Eureka, Eureka. Everyone just remembers that nonsense only. The thing is, Archimedes is actually famous, right? He is a weapons engineer, right? He is a military engineer, actually. He is famous for building weapons and weapon systems. No one actually cared about his science. Getting it? So the thing is, the king, right, during that time, He used to make pretty different weapons. Few of his weapons, right? One is the death ray, right? And another was, this what he called Hell's Fire. So they are one of the few things there. So death ray, right, was nothing but a concave mirror. When you focus the sunlight onto a ship ka sail or something, right, the sail used to catch fire. Now you need to understand during that time, right, in Greece and all these cities which are there, Athens, Sparta, right? I think there are another three more, whatever, Macedonia and all these things, right? See, during that time there was no internet, nothing. People were bored, so they used to like, like what to do. We are bored, so let's go for a war. So think of like that. It is PUBG during that time. So now PUBG we play it on phone, but during that time, let's take soldiers and fight for wars. People are literally bored, right? The only way you can achieve glory or something is to go fight a war and kill some people. So people just used to fight wars randomly. In that, Athens was one of the weakest city among the five. Athens is the weakest. So what these people used to do, first of all, right, it is all deception. They used to spread rumors. One of the rumor was this. The sun god Apollo, right, is protecting the city of Athens. If you try to attack that city, sun god will punish you. Now imagine, okay, today we have our army, tomorrow you're planning to attack them. And you heard this rumor in the city. Boss, if you attack Apollo, attack Athens, Apollo will come and attack you. We are like a bullshit here, don't take all this shit. Tomorrow we are going to occupy the city. So next day morning, we all took our ships and we started sailing towards Athens. And these people, right, used to have this big concave mirrors. They used to focus the sunlight and put it on ship ka sail. Now just imagine, you're coming on a ship and suddenly the ship ka sail catches fire in the middle of the sea. What is the first thing we will think of? Shit, Ray, Apollo is punishing us. This is true. The rumor is actually true. You're getting it out of nowhere when there's a fire. First thing you see is that only. Getting it? So that is there. So then people decided, like, let's go and attack in the night. There is another rumor. The Helga god Hades is protecting the city during night. So this is the main thing. You spread so many rumors and people will think it is false. And then when a small science trick will work. So somewhere, right, this Archimedes, he found an oil deposit. So what they used to do, he created trebuchets, catapults. And when he used to launch them with this oil ka thing, now imagine again, this fire comes and falls on your ship and the ship is catching fire because of the oil. Now, what is the first thing you do when there's a fire? You put water. But even after putting water, this oil will float on the water and the fire continues. It is a fire from hell, which cannot be extinguished. It is the Hades of fire. This is how you spread rumors. So people were shit scared actually to attack Athens. So this guy was famous for making a lot of weapons like this. So king used to give him a lot of money and say, Archimedes, do whatever you want, right? You're making good weapons and all. So this guy used to work on this research and stuff. So one day, right, the king gave some gold to a goldsmith and told him, this is a common story, like, and said, boss, make me a good crown. And the goldsmith makes a beautiful crown. The king likes it and everything. But then king gets a doubt. See, normally if you make something out of pure gold, right, it is very soft, right? It can easily bend. So what we do, we add some impurities. Generally, we add copper, right? You don't have 100% gold. You'll have little copper you add to make it stronger. So, but you can't find how much copper is mixed. Now, king got a doubt. Did this goldsmith steal some gold and added more copper than required? Now, how can you find it? One way, melt the crown. You'll find out copper and gold will separate out. But then crown will get destroyed. So he called Archimedes and said, oh, Archimedes, see, this is my problem I have. Take this crown, find out how much gold, how much silver is there, and let me know. Archimedes is like, what the hell, yaar? Matlab, you just ask anything out of me randomly. Like, how the hell will I know how much is there and all? But this guy takes the crown and now he's into serious thought. So during that time, right, they used to have these public baths. Anyway, it is run by slaves. So that is the thing. Any great kingdom in the past, right, the glory they got is because of slaves. And the reason these Romans used to go and attack everyone is because they can get more slaves. So this guy was sitting in a bathtub. He was sitting there and he felt something like, you must have noticed it when you're in a pool, right? You feel little weightlessness. So something struck him. That is where the thing comes. This guy started running on the road. Eureka, Eureka means I understood. I got it. So what did he exactly get it? So this was the thing. Now understand one thing. Archimedes, right? 2000 years back, he didn't have a concept of force or pressure or anything, right? But He's like a pure scientist, okay? It's mostly work and all. So this is what he said. This is what he felt. Okay, we have a liquid here. Consider an imaginary liquid. Consider an imaginary closed surface. So it is your imagination, right? Now, in this imaginary surface, the amount of liquid will remain constant. So for every molecule that enters, one molecule will leave. So the net volume is constant. This is the argument. If I draw FBD of this closed surface, now this is what he says. This closed surface will have some weight. So logically speaking, if you have weight, shouldn't you fall down? So the liquid will just should keep falling down. But we see it is at rest. That means there is someone who is exerting a force on this, who is keeping it at rest. Now see, this is all arguments, okay? Like now he does not know who is that someone. Then he says the only one who can exert force on this liquid must be the surrounding liquid, because there is no other way the force can come from anywhere else, right? And this is what we call as buoyant force. Now, if you ask Archimedes, right, why are you getting this buoyant force? He says, boss, I have no idea. The thing you need to understand, this thing was entirely experimental. He has no idea where is the surrounding liquid force is coming from. We know he's coming from this thing, but what exactly, he has no idea there. So this force, the surrounding liquid force, is equal to mg. Mass is nothing but density of the liquid, volume of the liquid into g. So this is what we call as the buoyant force. Is density of the liquid, volume displaced by the object into g. So buoyant force is completely an experimental quantity. We'll talk more about this. Exactly how did we get this? That we will see in more detail. All clear with this page? Clear? Then now he says, what if I replace this imaginary liquid with a solid surface? No, one thing is clear. The surrounding liquid, for some reason, is exerting force on this closed surface. Now understand, 2000 years back, like this guy had no idea about forces and pressures. So his argument is, since the shape looks same, the surrounding liquid force must not change, because the liquid does not know whether it is exerting force on a liquid or a solid surface. It will continue to do the same thing, rho L Vg. But now your weight mg will change, which is rho b Vg. If your density of the liquid is greater than density of the body, this will float. If density of the liquid is less than density of the body, it will sink. So whether you'll float or sink does not depend on your weight. It actually depends on the density. Think about this. When you see these huge ships, they're so heavy, right? Like they have weights of 50,000 tons, 60,000 tons. They still float. Now, the thing is, heavier objects sink, lighter objects float is a wrong statement. Denser objects sink and lighter objects float. Getting it? So when you take that ship, which is made of metal, but if you include the empty space inside, the density of air, the average density of the metal plus the air inside is less than density of water. Are you clear with this? If you see, if you take an elephant and if you take a rat and if you throw them in the water, whom do you think will die? If you take a rat and an elephant is heavy. If you throw an elephant and a rat in a water, what do you think will happen? The rat will sink and die. Because the rat has more muscle, it is more bones, it is more denser. On the other hand, elephant has more fat, and fat is less denser than water. Elephant's a very good swimmer. If you actually throw an elephant, it floats. That means in case you are a fat person, and if you are a thin person, the person with the six abs will sink in the water. The person who is a little fat and has more fat can actually swim much better. If you actually see the swimmers, right, they have a little tummy, they have a little fat, because that actually creates additional buoyant force. So elephants are pretty good swimmers. If you actually put an elephant in the water, they actually can swim well. Rats will struggle a lot. They have to put a lot of force. So there, in case you have little additional weight, you'll be a good swimmer if you go to a pool. But anyway, that is one. Great. Now, this is all the story from the Archimedes. Now, Archimedes has no idea why this came, but we can figure it out. So what is this buoyant force exactly? This buoyant force is actually due to the difference in pressure between the lower and the upper surfaces. So this buoyant force is not actually some new kind of force. The thing is, Archimedes didn't have the terminology to explain what it is. He just figured it out from an experiment. So if you had a body, if you try to see the pressure, the upper surface will have lesser pressure. But as you come down, the pressure increases. Right? So we get the force due to the lower and the force due to the upper. So this net lower force minus the upper force is your buoyant force. So buoyant force is nothing new actually. It is the same thing as your pressure into area. Right? So this thing is important. So whenever you draw an FBD, you have to be careful. So while you're drawing an FBD, either use pressure or buoyant force. Don't use both, because both are one and the same thing. You cannot use pressure and buoyant force in the same FBD at the same time. Or buoyant force, but not both. Think of like this. Let's say you have 1 lakh rupees in your bank account, right? And you wrote a check of 1 lakh on the same amount. How much money do you have? You still have 1 lakh, right? If you want money in the bank, don't think about the check. Don't use the check. If you want to use the check, forget about the money in the bank. They are not same. They're one and the same. Are you getting it? You can't say I have a check of 1 lakh and I have money in 1 lakh, so I have 2 lakhs. That doesn't make sense. So pressure is a theoretical thing. If you see pressure and everything, we literally drew it, right? Because of the collisions, you got pressure and everything, we could explain it. Pressure is theoretical, buoyant force is experimental. But they both are talking about the same thing. Just that Archimedes didn't have the terminology to use. Is that clear, everyone? What is buoyant force? So let me give an example. Let me solve a question with both of them using buoyant force and pressure. I think that should make things more clear. But any doubts on this page? All clear with this? Trishi, clear? Yashvi, Shriyansh, Advay, Advay, clear? Now, listen to this example. Let's say we have a container. You placed a block inside, cube. This is a cube of Seidel. Density of the block is rho b. Rho L is the density of the liquid. And let's say density of block is less than density of liquid, so it floats. So we want to find the depth inside the liquid. So x here is the depth of the block inside the liquid. Great. Now, when you solve this, there are two ways you can handle this. So whenever you solve a question, decide yourself like what you can do. Sometimes it is pretty easy to figure out which one to use, but let me do both. First, I'll do with bind force. I'm going to draw an FBD with the bind force. Now remember, when you use bind force, don't talk about pressure. So this is there. So this part of the cube is immersed in the liquid. So this red shaded area is the which is immersed inside. This is X, this is L, and this is L. So the bind force will act upward, which is density of the liquid, into volume displaced, which is X into L square into G. Agreed? The red volume is X into L into L. And your own weight, mg, is acting down, which is density of the body into L cube into G. That's it. Since it is in equilibrium, both the forces must be equal. Fp is equal to mg. From here, we add rho L x L square G is equal to rho B L cube G. We get x is equal to rho B by rho L into L. There. That is the depth of the block inside the liquid. All clear with this? Same question if I do with pressure. Now, the moment you want to say find pressure, don't talk about bind force. So the atmosphere is pushing you from the top, P naught into L square. The pressure at this depth, at an x, will be P naught plus rho liquid Gx, that is the pressure at the bottom, into area L square. And your own weight mg. So we get P naught plus rho L Gx L square minus P naught L square is equal to mg. If you actually notice something, this is the force due to liquid. Liquid is actually exerting this much force. And if you look at this term here, this net is your bind force. The net calculation here is your bind force. P naught will cancel. You end up with rho L G X L square is equal to rho B L cube G. We get x is equal to rho B by rho L into L. Same answer. But are you guys getting the difference? So the important statement here, the force due to liquid is not same as the bind force due to liquid. They're completely two different things. Sometimes they can become equal, but they don't mean the same thing. Force due to liquid need not be same as bind force. Is this clear, everyone? So examiner, they'll ask you like this, find the force due to the liquid. Most people will find the bind force and come. So in this question, if I ask you force due to the liquid, it is P naught plus rho L gx into L square. If I ask you bind force, then it is rho liquid into XL square into G. Both are completely two different things. Are you clear with this? So one of the confusion is that when you're drawing an FBD, some people what they do, right? They put pressure also, they put bind force also. Getting it? So both are not two different things. You're talking about the same thing. Any doubts on this? All clear with this, Rudransh? Aditi? Clear? Devanshi? Srihari? Clear? Anvita? Next thing. Few properties of this. So understand here, bind force is always upward. Again, remember what is up and down? Opposite to net force. Now, where does this bind force exactly act? The bind force acts on the center of mass of the liquid displaced. Meaning, for example, let's say we got a liquid here like this. And inside this liquid, we have a rod immersed. If someone asks you to draw the FBD of this, we will put mg here. Right, so this is the center of mass of the rod. Whereas for the liquid, if you see, this part is immersed inside the liquid, the green shaded thing. So this will be the bind force. So this will be the center of buoyancy. Is that making sense? If your weight is going to be equal to the weight of the displaced liquid, then you should be also acting on the center of mass of the displaced liquid. Meaning, if I have to give an example, suppose if you take a rod, x0, x is equal to L, and lambda is equal to lambda naught x. Do you guys remember the center mass for lambda naught x? 2L by 3, right? So the center of mass will be here, 2L by 3 comma 0. Whereas the liquid does not care whether the rod is uniform or non-uniform. You displace the liquid here. This will be the bind force at L by 2. Is that making sense, everyone? So if you dip a non-uniform rod into the liquid, the center of bind force and center of mass will be at two different places. Any doubts on this example? All clear with this? Next thing, normally whenever you keep a block on a surface, in reality, if you've seen at the bottom of the block, it is not perfectly rough. It will have small gaps here. So the liquid which it is present, so the liquid seeps into these gaps also. So there is a force due to the liquid from the lower side, and there's a force due to the upper side. There's a force due to the side walls. Right, so here the bottom surfaces will have small gaps. In reality, this is how the anything will look actually, because the surfaces are not perfectly smooth. But let's say if you have a block where the ground is perfectly smooth. How can this be done? There was a question like this in G. What they said, chapati ka dough is placed on the floor and a block is stuck to it. Glue basically, gum. So that gum filled up all the gaps between them and there is no water there. Getting it? And that gum started melting because of this surrounding water at a constant rate. So there is a question like that. And the radius of the gum started decreasing. At what time does the block leave the contact and flow off? There was a question of that sort. Now here, if you see, there is no lower force. There's no spaces here. Now think about this. There is no upward force only. Everything is pushing down. Bind force is not valid here. So if you want to use bind force, you have to make sure the whole thing, is the bottom part is surrounded with liquid. So there's no upward force. So here bind force is not applicable. It's okay if upper is not covered actually, but the bottom side there should be definitely there. So you have to be careful when can you apply the bind force and you can't apply bind force. So in these kind of scenarios, you have to use pressure to solve. If I give you one more example, let's say we have a container with a hole at the bottom, and this hole is actually closed with this is a hole. And you close that hole with a solid cylinder like this. So the solid cone blocks the hole. And now you started filling this with liquid. So I can ask a question like this, find the height of the liquid when the cone comes out of the hole. Now, if you look at the pressure here, the liquid is pushing you from the top. The liquid is also pushing you from the side walls. But once you are outside here, this is your atmosphere pressure P naught. This is a different thing only completely. So generally you can remember like this. If your lower surface is not covered with the fluid, you can't apply bind force. Generally, you can create some exceptions, but I'm not sure. Never seen a case so far. There might be some. Generally, bind force is not applicable. So this thing you will know when you do some few problems, right? You will get an understanding. Because think about this. What did Archimedes think? Archimedes said, imagine a imaginary liquid inside it, isn't it? And that was pushed by the liquid from all sides. Now here, some part of it is outside, which is being pushed by atmosphere. So you can't say the net force on the cylinder is due to the liquid. So then it is not bind force. Right? Is when bind force doesn't work. Clear with this, everyone? So when to use bind force, when to use pressure? Generally, if the surfaces are, it's pretty random surface, the area is, the surface ka shape you don't know, but generally it is bind force. If the surfaces are flat, you can generally do with both bind force or this thing. All clear with the theory so far? Let's see if you have problems on this. Yeah, that's about the bind force. So the main thing about this thing is when you use bind force, don't talk about pressure. If you want to use pressure, don't talk about bind force. So we have a container here, density of the liquid is rho L. We have a cube here. of side L, density of the block is rho b. Rho b is less than rho L. So this part of the liquid is immersed inside. This is X. So now what you did, container is accelerated upward. What happens to X? And what happens to X? What happens to bind force? And what happens to force due to liquid? Increase, decrease, remain same. And what if the container is accelerated horizontally? Then what happens to X? Happens. Try. You can answer here. I have no problem if you answer. Just if I don't reply, please don't spam. It's an easy one. What do you think will happen? Let's say if you accelerate vertically, what changes? Remember, G effective will change. So if you draw your free body diagram, so now your G effective will be G plus A. So G becomes G plus A. Right? So the bind force FB will become rho liquid XL square, this is X, into G effective. And this will be mg effective. The G effective term will cancel anyway. So rho liquid XL square G effective is equal to rho B L cube G effective. X will remain same. Rho B L by rho L. But bind force will increase, and the force due to liquid also will increase. What is the force due to the liquid? P naught plus rho G effective X into L square. So FB and FL will increase. What happens if you accelerate horizontally? If you accelerate horizontally, the liquid will become like this. As the block does not care whether whatever the liquid, the block will become like this. This would be the X. So the only difference will be G effective now will be root over A square plus G square. X remains same. So this X will not change whether you accelerate up or down, horizontally, it doesn't matter. Is that clear, everyone? Yeah, bind force will increase, the force due to liquid will increase, but X will remain same. Clear, Sudiksha? Anshika? Clear with this? Next thing. Let's say we have a container. We have a cylinder here. This filled with the liquid rho 1. This height is h1. This is filled with rho 2. This height is h2. This is h3. Let's do one thing. This is rho 1, h1. This is h3, rho 3. Outside the pressure is P naught. So the cylinder is floating. Okay. Solid cylinder of radius r. Floats in 3 liquids as shown. Find the bind force due to the liquids and the force due to the liquids. So there are 3 liquids. What is the bind force due to each liquid? Find the force due to each liquid on the cylinder. Let's get this. So I really want you to get very clear with that. Bind force and force due to liquid are not same. Because in the exam, in a hurry, right, you will write bind force and come, and they'll ask you force due to liquid. Bind force. Yeah. Right, Samir. What is the catch? See, if I draw the free body diagram of this thing, the bind force is easy. You just simply take the liquid displacement and finish it off. But if you look at the force here, the blue is exerting force like this, which will cancel out. The green is exerting force horizontally. That also will cancel out. The red is exerting force horizontally. That will cancel out. But there's a vertical component that will not cancel out. So force due to the liquid F1 is 0, F2 is 0, F3 will be P naught. You need to find the pressure at the bottom plus rho 1 GH1 plus rho 2 GH2 plus rho 3 GH3. That is the total pressure at the bottom into pi r square. This is the force due to the third liquid. Clear with this. But if you just want bind force, so FB1 is simply rho 1, a volume is pi r square H1 G. FB2 is rho 2 pi r square H2 G. FB3 is rho 3 pi r square H3 G. Clear with this. Now, one doubt we get is, right, if F1, technically, if you see F1 is not exerting any force, but you're saying the bind force is rho 1 pi r square H1G. How did that happen? If the liquid is not actually exerting force, why the hell are you getting a bind force in the upward direction because of F1, even though it's not exerting force? You're getting the point? If F1 is not exerting force, why are you getting bind force in the upward direction? Huh, Shreyansh? Shreyansh, are you there? Yeah, let's focus now. We can do yoga later. So, what is the thing here? Why are we getting that? Now, see, like I said, Archimedes, right, when he did the experiment, it was completely experimental. On the other hand, Newton's laws of motion, right, this is the thing. When I ask you find the force due to the liquid, it is always the direct force. Whereas the bind force is the effect of indirect and direct forces. I'll tell you the meaning. Listen. Suppose if the blue liquid was not there, if the blue liquid was absent, what would have happened? The pressure here, rho 1 GH1, would have been missing. Do you agree with that? If that pressure was missing, then the net upward force would have decreased. So the blue liquid is directly not exerting force, but what it is doing is the blue liquid is indirectly increasing the pressure at the bottom, and that pressure is pushing the cylinder up. Are you clear with this? So the bind force is taking care of that indirect effect. Meaning, to give an analogy, think of like this. Let's say there's a person A, there's a person B, and let's say there is some charity here. You are trying to donate some money. So A will say, boss, take 100 rupees from me and donate it. And B himself will add another 50 rupees and he donates 150 rupees to the charity. Now, if you ask Archimedes, how much did A give? What will he say? Archimedes is a practical person. He will say, okay, A gave 100, B gave 50. So this is the contribution. But if you ask Newton, boss, who gave the money? You will say A didn't give a single rupees to charity, whereas B gave 150 rupees. You're getting the difference. When you draw FBDs, we always draw the direct forces. We don't care about indirect contributions. Who gave money to charity? Simple question. B gave 150 rupees to charity. Done discussion. Are you clear with this? That is what FBD says. But Archimedes, right, like I said, 2000 years back, You didn't have a concept of force, pressure, and all. So he's being practical. A gave 100 rupees, B gave 50 rupees, so net contribution is 150 rupees. End of the day, the story is the same. Are you getting the difference? So if someone asks you what is a buoyant force, if you see here, F1 and F2 are actually zero, but they do contribute this much to the force. So that is the reason your problems will not go wrong. You'll get the answers. Is this making sense, everyone? Force due to a liquid and buoyant force due to a liquid. Clear? Pretty good one. So most people will, that's what I'm saying. If I ask you force due to F1, people will write this and come. So don't do that. So be careful. Now you have seen this. Any doubts on this concept, please ask me. Clear, na, Tanishka? Arya? Ovya? Clear? Advait? Can't see you, Advait. Your cam is blank. Let's see one more. Let's say we have a container fully filled with liquid, 2 row. Inside this, you kept a pendulum, 3 row. And you kept a pendulum, row. So this is pulling with tension T2. This is pulling with tension T1. V is the volume of the balls. Initially, system is at rest. If the system accelerates up, what happens to T1, T2? Increase, decrease, remain same. This is a pretty good mains question. What happens to T1 and what happens to T2? If system accelerates horizontally to the right, draw the position of the pendulums. I hope the question was clear. So we have a fully filled container, row liquid was 2 row. In that you kept a solid metal ball of 3 row and a ball of row. The tensions are T1, T2. If you suddenly accelerate this container up, what happens to T1 and T2? Option should be like that only. T1 increases, T2 decreases, both increase, both decrease, T1 decrease, T2 increase, remain same as options over. If the system accelerates towards right, draw the shape of the pendulums, meaning how will they align in equilibrium? No, yeah, that is wrong. Ishman, wrong. Arya, wrong. Right, Samyak? Now, understand one thing. Initially, system is not in, that forces are not balanced. If you look at that black ball, we have T1, this is mg, and this is your bind force. So your T1 will be mg minus bind force. Your mg will be 3 rho Vg minus bind force will be 2 rho Vg. That is rho Vg. Similarly, this guy, T2, mg, and this is Fp. Here T2 will be Fp minus mg, which is 2 rho Vg minus rho Vg. This is also rho Vg. Now, if you accelerate, your G effective becomes G plus A. Therefore, T1, T2 both will increase. Now, previously, why didn't it matter? That is because both were equal. See, think of like this. If you have 10 minus 10, if you multiply both of them by 2 and by 2, the difference will still remain same. But if it is 11 minus 10, and if you double this, and if you double this, the difference also will get doubled, isn't it? Because the forces were unbalanced, the difference also would have increased. So T1 and T2 both will increase. Clear with this? Now, what about the shape then? If the container goes horizontally with A, you know what is down. So this would be your G effective. The simple thing, denser objects will sink, lighter objects will float. So this is your denser object. This is your lighter object. So rho will be like this and 3 rho will be like this. So denser objects, point down basically. And what is down? G effective. Lighter objects point up. What is up? Opposite to G effective. Is that clear, everyone? So imagine you're sitting in a car and inside the car you have a helium balloon. If the car suddenly accelerates, the balloon will go which way? Front or back? If you have a helium balloon in a car and if you suddenly accelerate the car, the helium balloon will go which way? Front or back? नहीं श्रीहरि राइट हो गया right Utsa? Basically same logic. See, if you accelerate forward, then G effective will be this way. Since the helium balloon is lighter, it will point like this. It will go front. Clear with this? The helium balloon will go ahead. Think of this way. When you're in a car, the air surrounding the helium is denser, the helium is lighter. When you accelerate, all this air, which is denser, will go backward. So when it goes forward, the balloon will go forward. Clear with this? Think about this thing. In a washing machine, when you wash clothes, where will the soap ka foam go? Will the soap ka foam go to the center or edges? Soap ka foam is lighter, right? It comes toward the center, and the clothes which are heavier will go to the edge. Clear with this? So remember like this, denser objects will be in G effective, lighter objects will be opposite to G effective. So helium is lighter than air. Suppose if the balloon is filled with carbon dioxide, then what would have happened? Carbon dioxide is more denser than air, right? That would have gone behind the car. I hope you're getting the difference. So helium balloon and a balloon filled with carbon dioxide, they will behave differently. Kind of like this question basically. This is like a carbon dioxide balloon, this is a helium balloon, and this is your regular air, nitrogen, whose weight is almost 28-30. Clear with this? Take a break. Come back by 9:42. We'll continue from here. Any doubts so far?
Sir,
Oh, yeah.
sir, in the A part, if we take the force on the liquid, then even after
Force on the liquid.
if we take then tension would become internal and then we'll not consider tension. So
No, but the question is, why will you take the tension? See, if you consider the whole thing, the tension will cancel out only. You can't calculate tension.
Mm.
You want to calculate tension, right? So don't
Yeah.
make it internal, then don't make it internal.
But if we do that, then it will be like
It won't
after.
matter. Yeah, मतलब
Mm.
container का कुछ फर्क नहीं पड़ेगा ना. Net force, see, if this is T1, this is T1, they'll always cancel. Net force is always zero.
Ah, that
That won't matter, right? But that was not the question. Net force was zero because you got cancelled. That does not mean you didn't increase. I gave you
yeah.
100 rupees, I took back 100 rupees. Second case, I gave you 200 rupees, I took back 200 rupees. Didn't I give
Mm.
you more? I took more. So both are not same.
Mm.
Yeah. Chalo, come back in 5 minutes, everyone. Comes on, everyone. Let's go ahead. There, this is the Archimedes का thing. Let's get this. How does comes on? An ornament is weighing 36 grams in air and weighs only 34 grams in water. Assume that some copper is mixed with the gold to prepare for the ornament. I told you what is specific gravity. It's the gravity density with respect to water. Find the amount of copper in it. Any answers? No answers. See na. First of all, the mass is 36 grams in air. Okay. And now it weighs only 34 grams in water. So why did you lose that 2 grams? That must be because of the buoyant force. The F buoyant force must be 2 grams weight of water. So when you immersed it in the liquid, you lost the 2 weights because of that. This must be nothing but density of water into volume of the ornament into G. So that's 2 gram weight. So density of water is 1 gram per cubic centimeter. So from here, we will get volume of the ornament is 2 cubic centimeters. So when you immersed it in the water, it displaced a 2 centimeter cube of water, which is equal to 2 grams. So that's why 36 grams started looking like 34. You're done actually. After that, so let X centimeter cube be copper. Then mass of the ornament must be density of copper into X plus density of gold. That must be 2 minus X. The remaining volume must be gold. And then this is 36. Density of copper is 8.9x. Density of gold is 19.3 into 2 minus x. So this is 36. 19.3 minus 2. This is 38.6. Minus 19.3 minus 8.3. That is 10.4 x. Minus 2.6 is minus 10.4x. We get x is equal to 1 by 4 centimeter cube. That's 0.25. So 1/8 of the volume. So therefore, mass of the copper will be density of the copper, which is 8.9 into 1 by 4. That's approximately 2.2 grams of copper. So out of the 36 grams, someone mixed 2.2 grams of copper. Clear with this? This is what Archimedes did. Without destroying the ornament, you can figure out how much copper is there. Now, the only way to cheat this experiment is what? Now, the problem here is copper ka density is 8.9, right? You mix up 3 materials. If you can mix up 3 materials where copper is 8.9, gold is 9.3, and if you can mix up another material which is higher denser, like 22 or something, the average of this and this must become 19.3. Isn't it? If you can mix 2 impurities and impurity 1 and impurity 2 ka average density is 19.3, then this method will fail, isn't it? Because another impurity ka density also will become 19.3. You can't tell the difference between gold and this. But generally things which are denser than gold are like platinum and all that stuff. Even that is expensive. So yeah. Clear with this? Maybe you could actually mix up uranium. Uranium is pretty dense, but getting it is difficult. They do use, this.
Sir, is gold cheap or uranium cheap?
Uranium, there is this thing what he called depleted uranium is cheap. Normally, the enriched uranium is the one which they use in the reactor. After using in the reactor, that fuel is wasted. Basically, you have to throw it somewhere, but which is toxic. So what they do, they store it in special facilities, and it is expensive. So that is actually waste material. That literally it is a waste. But the thing is, they can't give it to you because that is still radioactive, and you can do all kind of dangerous stuff. So what people do, the army people do take it though. They actually use it in this thing. They use it in anti-tank missiles. When they make these anti-tank bullets, in the front of the bullet, right, they fill it up with depleted uranium. But because uranium is denser, for a given velocity, it has more kinetic energy. So if you have a tank, if you hit a tank with an iron bullet, this is what happens to the bullet. As the bullet hits, the bullet becomes like this. It opens up like a mushroom. So it does not penetrate the tank. But if you hit it with the uranium when it hits, right, it actually becomes pretty sharp. It penetrates the tank.
It can withstand more pressure, I guess.
It can withstand something like that. So it actually becomes sharp and it pushes through. So these are used for anti-tank bullets and anti-tank missiles. Yeah, but that whole area becomes radioactive, and that's a different story, though. But anyway, you're throwing it on your enemies, so we don't care. So that's the whole concept. You just pollute your enemy land and area with uranium. But yeah,
Boom, you win the war.
database there. Let's see. So that is one use case of depleted uranium. So we have two liquids here. Let's say this liquid density is 4 rho. This is another standard question. We have another liquid here, density rho. We have a block here which is suspended between the two liquids whose density is 2 rho. This is a cube of Seidel. So this part is immersed inside. This is X. Find X. So the blocker density is 2 rho. There are two liquids there, 2 rho and 4 rho. So you can't float in rho, you can't sink in 4 rho. So you're stuck in the middle. This is an easy question. Let's get this. Yeah, it was easy. So just draw the free body diagram. Again, you can use the pressure or bind force, but bind force works. So the upper part will be L minus X. The bottom part is X. So you can treat them as two bind forces. So the red one will have a bind force 4 rho X L square G. This upper liquid will have a bind force rho L square L minus X into G and your own weight mg, which is 2 rho L cube G. Balance them, you'll get X is equal to L by 3. One step, you're done. Easy? Yeah. All clear with this. Next one. We have a liquid here. Density is 3 rho. We have a cylinder. Area of cross section A. Height of the cylinder is h and density is rho. This thing is released from a height of 3h. Gravity is present. It's released from rest. Neglect any viscosity or neglect any force during collision with the water. You can ignore all that. Find the maximum depth the cylinder goes inside the liquid. So this cylinder will go into the liquid because of velocity, but liquid is denser. So eventually it will come out again. Find the maximum depth the cylinder goes inside liquid. Can you plot acceleration versus position graph? Taking the initial position as x is equal to 0, approximately plot acceleration versus position graph. Neglect forces during impact with water. You can ignore all that, only include mg and bind force. Let's get this. I hope by now you realized, right? Didn't the whole chapter has a very good vibe with NLM? It kind of looks like loss of motion only. Everywhere you're just drawing FBDs only. Let's get this. Cams on everyone. Others, do keep your cams on. Let's get the maximum depth. It's a good one. Let's see how you handle this. See, even before starting the problem, right? Take a minute, think about this, what is happening. Initially, when you're falling, there is no water, so you fall with G. Once you hit the water, will the buoyancy force immediately start acting? No, because the buoyancy force will depend on how much cylinder is inside, isn't it? That means as you keep going inside more and more, the buoyancy force also will keep changing. That means your buoyancy force is not constant. After that, once the cylinder completely goes inside, buoyancy force becomes constant. So the problem can be divided into three parts. Falling in the air, while entering the water, after completely entering the water. Are you getting it? So when you think about the problem, that is what I wanted to think for the first 1 minute. Don't worry about solving directly. Think step by step there. Let's see, Samyak. That might be the answer. I'm not sure. In the meantime, try to get the graph. But did you integrate or something? Samyak, did you integrate or did you get without integration?
I actually conserved energy.
Conserved energy. वो भी smart है. You can do that also. So you did what exactly? So work done by gravity, work done by buoyancy force is equal to the change in gravitational potential energy.
Yes, sir.
सही है. But the only problem with that, when you take bind force, how did you take the bind force during this intersection here?
I took initial and final states actually.
That is okay. But how did you take, what did you take actually? Initial and final state, ठीक है. This is your initial state, state 1. Finally, it stopped here, state 2. Change in kinetic energy, 0. Loss in potential energy will be, ठीक है, I'll take from bottom to bottom. So this is 3h and maybe let's say this is y. The loss in potential energy is 3h plus y plus mg. This is
Center
equal to
mass
work done.
3h plus h by 2 initial height. फिर बाद में
वो
h by 2
ठीक है,
सब.
चलो जो भी height ले लेंगे. Now this is equal to work done by external forces. What is the external force here? Bind force.
हाँ.
अभी bind force is not constant, no? But so how do you take work done by bind force? You took bind force into this y, na? So मेरा question ये है, so while you are entering, there is a bind force here also, na?
Yes, sir.
So how do you take constant for? I agree. After entering, it is constant. You could have done that, but while entering, what did you do?
I missed that actually.
वो entering part छोड़ दिया ना. Listen, I'll show you the picture. What is happening?
Sir, can I answer that question, please?
बोलो ना.
Sir, actually, there is one more loss in energy that we haven't counted there.
Which one?
Sir, it's the change in energy of the water.
वो तो negligible है ना हमने. We are assuming water level is not changing.
Sir, not that one. When the
Okay.
cylinder went inside the like the water, it took out
This
some
cylinder
part
part
of
of the
that.
water actually it came to the surface here.
Yeah. So that part of energy has been lost. Like if we are assuming that the
वो
water
भी
level
include
has
करना
increased,
पड़ेगा.
so
हाँ,
that
Samyak.
energy we are allowed to include in that.
Samyak, understood what he's saying? He's saying this
Yes.
thing. See, when the cylinder is falling, the cylinder is coming and occupying this water, na? This water will go to the surface level, isn't it? Matlab, the loss in potential energy of the cylinder is also the gain in potential energy of the water. वो भी include करना पड़ेगा उसमें. That is a good one. That वो भी है. Because when this is displacing water, that water should go somewhere, na? Where it is going? It is going onto the surface. So the cylinder is losing potential energy, but the water is also gaining potential energy. So yeah, I think, let's see, I'll do with forces though. Energy, I'm not really that confident. So initially you're falling with G. So listen to the problem, what is happening. So first you're falling in the air, 3H. First I'll just draw the pictures. Then you're hitting the water. So this is one state, you're in the air. At this point, you must have gained some velocity, V1, which is root over 3G, 3H. Sorry, 2G, 3H. Everyone agrees with that? V square minus U square is 2AS. So this is the velocity of the cylinder just before hitting the water. After hitting the water, the cylinder will be entering inside like this. Let this be X inside. At this instant, if you look at the forces, we have the buoyant force FB, which is 3 rho, area xg, and your own weight mg, which is a rho a h g. That means acceleration here will be upward actually. So because of this, you will have a deceleration in the upward direction, which is FB minus mg is equal to mass into acceleration, which is 3 rho a xg minus rho a hg is equal to m is rho a h into acceleration. Rho a will cancel everywhere. You will get 3x by h g minus g. You can take out g common. You will get 1 minus 3x by h. So that is a deceleration in the upward direction. Then we can write a is equal to minus v dv by dx because you're decelerating. Then when you integrate this integral v dv. So now I'll just draw this thing. So this thing will enter inside completely. This is the scenario when you completely enter inside. At this point, your speed will be v2. And then finally, you will come somewhere here and eventually stop. So this is the depth we are trying to find. Why? Are you getting the picture, everyone? So when you integrate this minus v dv, this limits will go from v1 to v2. So this is the acceleration only while you're entering. Once you completely enter, you can't use this acceleration anymore. This is an acceleration while entering the liquid. So minus v dv is equal to g into integral 3x dx by h minus dx. This will go from 0 to h. v2 square minus v1 square by 2 is equal to g into 3x square by 2, that is 3h square by 2. 3h by 2 minus h, that will be h by 2. 2 will go off. We get V2 square will be V1 square minus GH. V1 square will be 6GH, so that is 5GH. That is the speed just after entering inside the water. So here V2 is the speed just after the cylinder completely enters. सेकंड टर्म क्या कह रहा है? माइनस mgx plus u minus 3p m by p.
Sir, I removed the part of the water, the gravitational potential energy of the water,
वो
which
ठीक है,
was
मेरा
not.
एक ही कंसर्न है, when you are entering the buoyant force is not same, how are you including that?
Sir, it does not matter. We have to just conserve
You
the
are just taking the
initial energy.
potential energy.
Yeah. क्योंकि energy will always remain conserved.
सही है. नहीं, actually इसमें वो हो रहा था, the work done by the buoyant force is actually used to increase the potential energy of the water.
Yeah.
That term got cancelled there. Anyway, let's see this thing. I'll show you that method also, what Arya did. That was also good. That is faster actually. But so far clear, everyone, what is happening in this scenario? This is still not an advanced question. Huh? You know what is the advanced question? They'll ask you find the time period of oscillation. So we can actually do that in SHM. That would be an advanced paragraph question. But anyway, we got the speed 5GH. Now what? So I got V2. Now once you are completely immersed, now what are the forces? mg, fb. Now we have a constant deceleration. So mg will be rho a hg. 3 rho hg minus rho a hg is equal to rho a ha. So we get a is equal to 2g. So once you are completely inside, you are decelerating with 2g, then I can use v square minus u square is equal to 2as. The final speed is 0, u square will be 5gh. Deceleration is minus 2g, and this is your y. So we get y is equal to 5h by 4, which is the same answer you got, Samyak. That's because you did 2 mistakes and somehow they worked out. Are you
Minus
clear even
minus
what we are doing?
plus.
कुछ तो हुआ. Yeah, I think what happened now, that variable force which he took, right, that became the change in potential of the water. He ignored that here, he ignored the work done here, both got worked out.
I mean, yeah, both are same, I guess.
they दोनों सेम हो गया वो. Yeah. Is this clear, everyone? Clear what we did, but did you get the whole process? While falling in the air, A is G is constant, you know how to do. While entering is the headache part. While entering, this is the scenario. You have to integrate and get this. Once you completely enter also, it is easy because A becomes again constant. You can finish off with kinematics. Clear with this? But anyway, we need to do this, Arya, because the second question is A versus X graph. तो ये मेथड तो करना ही पड़ेगा, even the energy is safer. Let's see. All clear with this? What about the acceleration? Now you can do this acceleration, but the method what Arya said, that was good. I'll show you that with another problem. So you're plotting A versus X graph. I will take up as positive, down as negative. So initially you're falling down, so acceleration will be negative. This is minus g, you're in air inside. So at this point, while entering, look at this acceleration here. The buoyancy force is upward, so acceleration is upward. You will increase. So this black line is the situation while entering. So once you are entering, the acceleration is decreasing than g. And once you completely enter, you are this scenario. This is inside the water. Once you're inside the water, again, acceleration becomes constant. Which we calculated, this was 2g. And then it repeats again. So After this, once you start coming down, this is again coming out. Then again you start flying in the air. Then again you go up. So this will keep repeating. This is how the graph would look. Clear with this, everyone? So while entering and while leaving, the acceleration would be a linear function. Any doubts on this? Yeah. All clear with this? Same question. Let's do this with that energy method now. I think this would be the question. You take a solid sphere. Density rho. Three rho. Radius r, and let's say this height is 2r. Find the maximum depth the ball goes inside the liquid. Take it as a 3r only for safe side. I don't want it to stop somewhere in the middle. Now, if I try to use my calculator method, it becomes a mess. You can't integrate this. Let's see how will you do this.
Sir, how much the center of mass goes inside, right? Not anything else.
Same
The
here, na,
outer
right?
edge.
Same only, na. Whatever the center of mass moves, outer edge will go the same distance. Find the maximum depth sphere. ठीक है ना, you can say whatever you want. You can say from center of mass, you can say from the outer edge. I
Okay,
understand
sir.
your point. Max depth, center of mass, लिख लेना. Center of the sphere. It's fine, na, because in the previous question also I took y from here. Na. If you include the bottom, then it would have been y plus h extra. It depends on how you're putting the answer. So someone did say y plus h actually. No. How to handle this? Now here, integration is a bad idea because as you enter, the area of cross section will keep changing. It becomes a mess. Think for a minute, then I'll tell you what was the idea there. Let's see. Now listen, what was the idea that these people are talking about? So as this sphere goes and falls in the liquid, let's see the final scenario. Finally, the sphere would have been somewhere here. The sphere would reach somewhere here. And finally, it came to rest. Initially, it was at rest. And you're saying there's no dissipation of energy. Mg is a conservative force. Bind force is also a conservative force. Now, the question comes this. What happened to all the liquid that was displaced here? Liquid that got displaced must go somewhere because the volume has to remain same. Liquid displaced by the sphere It must have gone somewhere. Where will it go? It must have gone to the surface. Technically, the lake water level should have increased, but we will ignore that. So all the water that was placed here, so this ball came in that position and the liquid got displaced, it must have gone to the surface. Is that making sense? Yeah.
So we can say we are compensating that lost energy by adding an extra term.
Let's see. Let's think here. Clear with this? Now, initially your velocity is 0, finally your velocity is 0. So can I say like this? The potential energy lost by the ball is potential energy gained by the water or gained by liquid. Is that statement making sense? Think about it. Where else will the energy go? There is no kinetic energy. There is no dissipation. There is nothing. So whatever energy you lost must have gone somewhere. Clear? Now, if I take the center of mass from center to center, how much will that be? This was r, so that was 4r, and let's say this height is y from here, from the center, so this is r. You could take y from wherever you want. So that would be mass of the ball mg. The total height it lost was 4r, 5 plus r, y plus 5r. That must be equal to mass of the liquid. So the center of mass of the liquid must have gone mg y plus r. Is that clear, everyone? Because the red sphere as actually liquid, isn't it? The red sphere liquid went up. This thing went to the surface. So mg y plus 5r mass of the liquid g y plus r. So mass of the sphere was rho, volume 4 by 3 pi r cube g. It will cancel anyway. Mass of the liquid would be 3 rho, volume g y plus r. Rho vg goes off. This would be y plus 5r. Will be 3y plus 3r. So that would be 2r is equal to 2y. So y is equal to r. From the surface. So if you take from center to center, the answer is 2r. Is this making sense, everyone? Arya, did the same?
Yes, sir, kind of.
Kind of. तो क्या किया exactly then?
Sir, I took it from baseline. Yeah, right.
वो
Same.
ठीक है ना, that won't make a difference. You are saying this is y.
Oh, yeah, okay. Yeah, I
वो
did
ठीक
the
है ना,
same thing.
same thing. But is this logic clear, everyone? So if they had to ask you only the depth, right? Even the previous question you could have done like this, isn't it? The only difference would be in case of mass of a sphere, you have to take mass of a cylinder. That would have still got volume would have still got cancelled anyway. It wouldn't have mattered. Clear na Samyak? This is the conservation of energy, I think.
सर एक्चुअली मैंने थोड़ा अलग किया था बट उससे भी सेम आंसर ही आया वापस
क्या किया था तूने?
मैंने सरफेस के रेस्पेक्ट में पोटेंशियल एनर्जी लिया था तो
Okay.
ऊपर जैसे कि उसके इफेक्टिव जो एक्सीलरेशन है जी होगा तो फिर उसमें m लगा है और फिर पानी के अंदर उसमें भी कुछ एक्सीलरेशन होगा जैसे 2g है तो उसमें भी ऐसे
Right.
y है तो फिर y प्लस r इंटू 2g इंटू
तो वो क्या हो रहा है ना? Because the shape is symmetrical ना, while coming and going back, it is working out for you.
ओके
It is working out for you. It is because see, even if you take a random shape now, what happens? See, but for a sphere, right, up and down are symmetrical, isn't it? We need to check
Yes.
whether it will work for a cone. So, anyways, but clear, na, that method what you did might be giving the answers, but there is still some issues there.
ओके सर
Arya.
Sir, can you please explain the term which you wrote, like mass liquid into y plus r?
Basically, in this ball ka place mein, there used to be liquid, right? that sphere, that center of mass of this went to center of mass on the surface, na?
Right.
So that gain in potential energy is mg y plus r.
Okay.
Basically, sphere became a flat surface.
All right. Sir, I actually didn't think about it like that. I thought कि मैंने उस पानी को निकाल ही दिया and instead of
Okay.
that पानी मैंने उसका एनर्जी रिप्लेस कर दिया इक्वेट करने के लिए दोनों साइड पे
With two rows है.
और जो कुछ भी उसका एनर्जी था at
Uh,
that point.
ठीक है, if you're confident with that. This way I'm more confident with this.
Okay,
Meaning
sir.
ये clearly दिख रहा है ना, this liquid must have gone to the surface, so this was the change in potential energy of the red liquid. Basically, you
Right,
made the
sir.
sphere into a flat surface.
Yes.
Oh. Let's see one more. We got a cylinder here with a cavity inside. So someone removed a scoop. This is a solid cylinder with a hemispherical cavity. And this entire thing is filled with liquid. When you fill with this liquid, even inside the cavity, there is a liquid. Density of the liquid is rho. The height of the cylinder is h. Radius of the cylinder is r. This is the string. Right? And mass of the block is m. Now what happens? The liquid inside will not keep quiet. The liquid will exert force on this curved surface. Right? So meaning if you look at the shape here, so inside this cavity, the liquid is pushing this curved surface like this. And remember, pressure is not constant, it changes with depth. So this will exert a force on a curve. Find the force on the curved surface. System is in equilibrium. Find force due to liquid on curved surface of the cavity. How do we do this? There's no need to integrate. I'll give you an idea. Say, draw an FBD with bind force, draw an FBD with pressures. Now see what I'm asking here, force on the curved surface. Matlab, this is the force due to the liquid. So if I want force due to the curved surface, I can't use bind force. You're getting? If you find force on any one surface, matlab bind force is gone because the bind force is a net resultant of force on all surfaces. You cannot just take one part. Draw an FBD with bind force, draw an FBD with pressure. Try. I'll give you a minute. If you draw that, you will get the answer. You will clearly see what is bind force there. When you draw FBD with bind force, tension, mg, bind force. That's it. Now, if you do FBD with pressures, tension, P naught into area. This is your F curved, and this is mg. Now, think about this. Technically, isn't both the diagrams same? So tension का place में tension is there, mg का place में mg is there. So FB का place में you have P naught pi r square and F curved. And isn't that the definition of bind force? It's a difference in force due to the lower and the upper surfaces. So you can clearly see here, tension plus FB is equal to mg. So here tension so FP is mg minus tension. So here tension plus F curved is mg plus P naught pi r square. So you need not even draw the FBDs. If you remember that, you can argue the force on the curved surface and the force on the upper surface, that difference must be the bind force. This is mg minus t. Check equation 1, equation 2. RHS is same. So the bind force must be, so F curved is F bind force plus P naught pi r square. And what's the bind force? Density of the liquid. The volume of the cylinder is pi r square h minus that cavity 2 by 3 pi r cube into g plus P naught pi r square. Is that clear, everyone? Anyway, the horizontal forces will cancel, so we don't include them. So the force due to the lower surface and the force due to the upper surface, that difference must have been the bind force. Is this making sense, everyone? There, that's how you do this thing. Do check it out. Again, if you see, there's a lot of NLM. This is what I was saying. Clear with this? So there, that would be the last one for the day. Next class, when we catch up, we'll continue from here. We'll see a few more problems on this thing. It's called, this chapter is actually called fluid statics because the liquid is not moving, right? And in the next class, we will finish all this part and we'll start off with fluid dynamics. What happens when the liquid starts moving? So we will see all that stuff, Bernoulli's equation and all that thing. So, okay, with that, we'll wrap up for the day. I'll see you guys again on Thursday, same time. So